Good afternoon, everybody. My name is Ulises Nunez, and I am a PhD student at Georgia Tech under the supervision of Dr. Glenn Lightsey at the Space Systems Design Lab. And today, it is a huge honor to present to you on the topic Mahalanobis shell sampling method for collision probability computation. We will start this discussion by motivating this work. Spacecraft formation flying is a set of more than one spacecraft that track dynamic states relative to one another. Having such an arrangement of spacecraft is beneficial because it can endow missions with improved scalability and maintainability. It also has many potential scientific applications. Collision avoidance is a necessity in formation flight because of constant kinetic threats to any formation, both from external debris and among agents in such formations due to drifting or maneuvering. Active collision avoidance schemes focus on monitoring collision risk, checking safety criteria violation, and, where needed, planning and execution of dedicated collision avoidance maneuvers. In these charts, you see conceptual illustrations of probability density functions, or PDFs, of the relative position between two agents. One type of collision risk indicator is misdistance, which is any statistical description of the physical separation between two agents, as seen on the left. The other type of collision risk indicator is the probability of collision, which is the probability mass of the relative position which is inside of a collision region. Collision risk is mitigated by setting constraints in an optimal control problem in terms of these indicators. This work focuses on one type of probabilistic collision risk indicator, namely the kinematic or instantaneous probability of collision. Accounting for realistic effects in relative orbital dynamics generally makes those dynamics quite complex. Therefore, particle methods are attractive in order to propagate a relative dynamic state through arbitrary processes. However, because uncertainties in relative orbital environments tend to become large when compared to agent dimensions, active collision avoidance maneuvers could be triggered by low-valued probabilities of collision. Therefore, traditional particle-based propagation could become quite costly when trying to reproduce those low-valued probabilities of collision. This work aims to develop a general methodology for particle sampling from tails of normal probability distributions that allows for arbitrary propagation without unduly penalizing sample size. First, we will discuss the idea of a characteristic length or hard-body radius for some agent I, denoted by Li, which we define here to be the furthest Euclidean distance from its center of mass to any point in its body, preferably under a worst-case configuration of all appendages and deployables. Then we make the hard-body radius assumption, which simply holds that the body of agent I can be approximated by a ball with radius Li centered at the center of mass. This is a conservative assumption that also simplifies the definition of collision events. It should be noted that these balls are surrogates for the size of the object, and they are not position PDFs. With these notions, we define a collision event as the condition when distinct agents occupy portions of the same volume of space at the same time, that is, when their circumscribing balls have a non-empty intersection. Alternatively, a collision occurs when the distance between centers of mass is less than the sum of their hard-body radii. We define the intersection or collision volume as a region of relative position space in one, two, or three dimensions where the collision event occurs, that is, all points in relative position space whose distance to the origin is less than the joint hard-body radius. Then, we define the kinematic probability of collision, or KPC, as the instantaneous probability of the collision event as previously defined. If the probability density function, or PDF, of the relative position is known and continuous, the KPC can be computed as the integral of the relative position PDF over the intersection volume. In this slide, we illustrate the concept of KPC computation from PDFs. In this particular example, the dynamic system has one-dimensional relative position and relative velocity. On the left, we see the KPC being computed from the relative position PDF. On the right, the KPC is computed from the joint PDF of the relative position and relative velocity. Both computations are identical, yet each has its own advantages. On one hand, since the KPC only depends on the relative position, computing the KPC from the relative position PDF is not only correct, but it is a much more straightforward operation than computing the KPC from the full relative state PDF. On the other hand, if we are concerned with the dynamic evolution of the relative state, especially if these changes are quantified through a particle-based method, then it makes sense to compute the KPC from the full relative state PDF. Let big X be a normally distributed random variable. Additionally, let big X be non-degenerate, that is, with a positive definite covariance matrix. The Mahalanobis distance of an instance little x of a random variable big X is essentially the covariance ellipsoid of big X to which little x belongs. The concept of the Mahalanobis distance generalizes the idea of 1 sigma, 2 sigma, 3 sigma, etc. to higher dimensional normal probability distributions. In this work, we also introduced the notation of the Mahalanobis volume, which is the set of all points within a certain sigma from the origin, and the Mahalanobis contour, which is the set of all points away from the origin at a certain sigma value. A theoretical result from the literature is that the probability mass within a volume bounded by a surface of constant Mahalanobis distance is an analytical function only of the Mahalanobis distance of the boundary of that volume, regardless of the parameters of the distribution and regardless of dimensionality. Then, we define the Mahalanobis shell as a region bounded by two surfaces of constant Mahalanobis distance. Of course, the probability mass in a Mahalanobis shell is a unique function of the Mahalanobis distances of the bounding surfaces. This slide introduces the concept of the Mahalanobis shell sampling algorithm, or MSS. The first step is to generate a uniform sample of the unit hypercube. This is generally achieved through a quasi-random number generation algorithm for unit hypercube sampling. Using the sample, we perform an area per survey mapping from the unit hypercube to the unit hypersphere, which yields a quasi-uniform unit hypersphere sample. Then, using the statistics of the normal random variable to be sampled, the hypersphere sample is transformed into a sample in a Mahalanobis shell for several Mahalanobis shells. In this slide, we are doing an MSS sample of a three-dimensional normal random variable. However, this method is general in that it is applicable to samples in any finite dimensional space. In this work, we are assuming that the initial relative state has a normal probability distribution. The MSS algorithm can be applied to KPC computation as follows. First, we specify the parameters of the sample, the number of shells, the number of samples per shell, and the maximum Mahalanobis distance Dmax. Next, an MSS sample is made of the initial relative state with these parameters. Then, the sample is propagated through arbitrary dynamics. The weights assigned to each point in the sample are proportional to the probability mass in the Mahalanobis shell and inversely proportional to the amount of points in each shell. By doing this, we are able to directly sample from tails of normal probability distributions without unduly penalizing sample size, as would occur in a Monte Carlo method. Finally, the KPC is computed as the sum of the weights of the particles that meet the collision condition. As a proof of concept, in this work, we apply the MSS KPC computation methodology to a dynamic system based on the relative motion of two one-dimensional spring mass damper systems, and we assume a normal initial state distribution. We use this pedagogical example because we can find an analytical expression for the KPC in terms of the distribution statistics and the error function. An example KPC waveform to be reproduced is shown in the slide, and its parameters can be found in a manuscript. The metric we use to compare the analytical and MSS KPC waveforms is the discrete time difference root mean square, or discrete time error RMS. To make comparisons tractable, we fix the number of particles per shell. We do two performance traits. One, by changing the number of shells while fixing the max Mahalanobis distance, and vice versa. In the first performance trait, we find that for a sufficiently high max Mahalanobis distance, increasing the number of shells monotonically increases accuracy. This makes sense because doing so is similar to having a finer grid of sample points. In the second performance trait, we find that for a fixed number of shells, increasing Dmax improves accuracy up to a point, after which residuals start deteriorating. This makes sense because increasing Dmax while keeping the number of shells constant makes the grade of sample points more coarse, even though it does include more probabilistic outliers. In conclusion, the Mahalanobis shell sampling algorithm, or MSS, was developed in order to directly sample outliers from any normal probability distribution in finite dimensions. Then, we applied MSS to computing the kinematic probability of collision, or KPC, in a low dimensionality dynamic example. The main lesson from KPC residuals to be learned is that increasing the number of shells is needed when sampling for more extreme outliers. Thank you all so much for watching this presentation, and I look forward to your questions.